Right now, in this exact moment, you're spinning through space at 67,000 miles per hour. Not metaphorically. Actually, your planet, your galaxy, everything you've ever known is hurtling through the cosmos at incomprehensible velocity. And here's what will blow your mind. Even at that insane speed, it would take our fastest spacecraft 230 million years just to cross our galaxy. Our galaxy, not the universe. Our galaxy. I'm sitting here telling you about the Milky Way, and by the time I finish this sentence, you will never look at the night sky the same way again. You'll understand that you're not just living on Earth in our solar system. You're living inside a cosmic island so monumentally massive that your brain will struggle to process it. And then, I'm going to show you something even more terrifying, that our galaxy is, honestly, kind of average. Before we go anywhere, I need you to do something. Hit that subscribe button right now. This information is going to rewire how you see reality, and you're not going to want to miss what's coming. Plus, I'm genuinely curious. Where are you watching this from? Drop a comment with your country and what time you're watching. I read every single one, and knowing you're out there, somewhere on this pale blue dot, looking up at the same stars I am, makes this feel less lonely. Also, if you're watching this at night, I want you to do something after this video. Go outside, just for 5 minutes. Look up. And when you do, remember that what you're seeing, those few thousand stars, visible to the naked eye, is less than 0.0000001% of what's actually there. You're looking at the surface of an ocean and thinking you understand water. That's what we're about to fix. Before we dive deep, hit that like button if you love space content. Let me know in the comments, what's your biggest question about the Milky Way? What keeps you up at night when you think about space? Because I'm going to answer the questions you didn't even know you had. Here's where most people get it wrong. When you hear galaxy, your brain probably conjures up those beautiful spiral images from the Hubble telescope. These elegant, delicate-looking pinwheels floating in the void. We're trained to see them as discrete objects, like islands in space. Clean, separate, manageable. But that's where our first mind-blown moment hits you. The Milky Way isn't elegant. It's not delicate. It's grotesquely, incomprehensibly massive. Think of it like this. You know how from high altitude, a storm system looks small? But when you're in it, rain is everywhere. Wind is everywhere. Lightning is hitting everywhere. That's our galaxy. We're not observers. We're embedded in its chaos. We're weather inside the storm. When Galileo pointed his telescope at the night sky in 1610, he discovered something that shattered the medieval conception of space. He didn't just see stars. He saw hundreds of stars clustered together in regions that appeared as fuzzy patches to the naked eye. These weren't errors in perception. These were stellar populations so dense that light couldn't resolve them individually. Galileo had just glimpsed the structure of our galaxy, though he didn't yet understand what he was seeing. Fast forward to the 1920s. Edwin Hubble, yes, the Hubble Space Telescope is named after him, made an observation that changed everything. He proved that the Andromeda Nebula wasn't part of our galaxy. It was a separate galaxy, equally massive, 2 million light-years away. This single discovery expanded our universe by orders of magnitude. Overnight, humanity went from thinking the Milky Way was the entire universe to realizing it was just one among billions. But here's the thing that most documentaries don't tell you. Hubble's discovery made our place in the cosmos simultaneously more profound and more humbling. We weren't the center. We weren't even the largest galaxy in our local neighborhood. We were medium, average, ordinary. And yet, within our ordinariness, we contained incomprehensible wonders. Think of it like this. Imagine you're a single cell in your body. Your cell has been told that it's the entire universe. Then one day, you realize you're actually one of 37 trillion cells in a being that contains an entire mind, consciousness, and self-awareness far beyond what a single cell can fathom. That's what Hubble's discovery did to us. We weren't special anymore, but we became part of something infinitely more spectacular. Now, here's where it gets dangerous. Once you truly understand the scale of our galaxy, once it stops being an abstract number and becomes something visceral, you start asking questions that don't have comfortable answers. Questions like, how many planets are in our galaxy? How many might host life? How are we even having this conversation if space is this vast? These questions are going to haunt you. And in the next section, we're going to answer them with numbers so large that mathematicians had to invent new ways to talk about them. The Milky Way isn't waiting for you to understand it. It exists at a scale that exceeds human intuition. But I promise you this, by the time we're done, you won't just understand the numbers. You'll feel them in your bones. What if I told you that astronomers have been measuring our galaxy wrong for decades? Not just slightly off, fundamentally wrong. We've been getting the size estimates increasingly correct through the 20th century, but every time we update the measurement, it gets bigger, sometimes massively bigger. In the 1930s, we thought the Milky Way was about 100,000 light years across. That seemed impossibly vast. Our fastest spacecraft would take 10 billion years to cross it. Today, we know that was embarrassingly small. Current estimates place the disk diameter at somewhere between 200,000 and 250,000 light years. Some recent data suggests outer regions extend even further, possibly up to 1 million light years when you include the complete dark matter halo. Do you understand what just happened? We doubled our estimate of something you can't even see with the naked eye. We found out we were looking at a fraction of the actual structure. Imagine if tomorrow, scientists announced that Earth was actually twice as big as we thought, and there were entire unknown continents underneath where we're standing. That's what happened to the Milky Way. We're still finding new structures. Here's the specific revelation. In 2019, an international team led by researchers including members from the International Astronomical Union announced something shocking. They discovered that the outer disk of the Milky Way is actively warped and rippling. It's not a flat pancake. It's more like a warped, undulating piece of fabric, bending and twisting in ways we didn't predict. And the cause? A collision. The Sagittarius Dwarf elliptical galaxy, an entire galaxy, has been colliding with ours, passing through our disk for the past billion years. Think about that. Our galaxy is in a collision we didn't even notice until a few years ago. We're not stably orbiting. We're being consumed slowly by a smaller galaxy, and the gravitational waves from that collision are rippling through our entire structure. Now let's talk about the actual scale in numbers that your brain will hate. The Milky Way contains somewhere between 100 billion and 400 billion stars. That's not a typo. We can't narrow it down more precisely than that. That's like if I asked you how many grains of sand are on Earth, and you said somewhere between 1 billion and a quadrillion. It's massive uncertainty at an incomprehensible scale. Think of it like this. If every human on Earth right now, all 8 billion of us, started counting stars from the Milky Way at the rate of 1 star per second, without stopping, without sleeping, we would need 1,300 human lifetimes to count them all. And we'd probably get the number wrong anyway, because we can't even see half of them. But it gets better, or worse, depending on your perspective. Johann Galle in 1846 discovered Neptune, the first planet found through mathematical prediction rather than observation. His work depended on understanding gravitational systems. Today, we use that same principle on a galactic scale. Vera Rubin in the 1970s made observations that fundamentally changed our understanding of galaxies. She was measuring how galaxies rotate, expecting to see them slow down at the edges like a record spinning. But something impossible happened. They didn't slow down. The rotation curves remained constant, far beyond where they should have. This was evidence of dark matter. Dark matter, the universe's deepest mystery. Something that outweighs all the visible matter in the Milky Way by 5 to 1. Invisible, undetectable directly, but gravitationally overwhelming. Think of the Milky Way like this. Imagine you're watching a dancer. The dancer is visible, beautiful, performing incredible moves. You assume they're performing alone. Then you realize from the way they move, from how they interact with empty space, there's an invisible partner. A partner 5 times more massive than the dancer you can see. They're holding up the visible dancer, spinning them, guiding their motion. You can't see the partner, but you know they're there because of how the dancer moves. That invisible partner is dark matter. It comprises 85% of the matter in our galaxy. Everything we can see, every star, every planet, every bit of matter that's ever mattered to humanity makes up just 15% of the mass of the Milky Way. Let me hit you with another number that will recalibrate your sense of scale. The Sun, that massive ball of nuclear fusion that we orbit, that seems impossibly large when you stand under its rays, is utterly average. It's not in the top 90% of stars. It's somewhere in the middle, maybe slightly smaller than average. And yet, the Sun is so massive that 1.3 million Earths could fit inside it. The Sun is unremarkable. And inside the Sun, at any given moment, the core is converting 600 million tons of hydrogen into helium every single second. Every single second. That's not a metaphor. That's actual mass. The Sun is literally vaporizing our planet's entire mass in fuel every few seconds, and it will do this for another 5 billion years before it dies. Our Sun is one of 100 to 400 billion stars in our galaxy, and the Sun is, relative to most of its siblings, kind of unremarkable. Now you're starting to feel it, aren't you? That vertigo, that sense that your brain doesn't have adequate categories for these numbers. That's not a failure of comprehension. That's accurate perception. These numbers are too big. They exceed human evolutionary experience. Here's what's about to happen in the next section. We're going to stop thinking about the Milky Way as a number and start thinking about it as a place. A place with structure, with regions, with neighborhoods. And that's going to make everything suddenly feel more real. Because there's an even more shocking part about the scale of our galaxy. It has a center. And that center is actively destructive. There's a supermassive black hole at the heart of our galaxy that's so massive, it warps the very fabric of spacetime. And we're orbiting it. 230 million years per orbit. Our Sun, and every planet we know and love, is in a stable but deadly orbit around something so extreme that not even light can escape its gravity well. In the next section, we're going to get up close as we can to the most extreme object in our galaxy. And you're going to understand why it exists and what it means for us. There's something in the center of the Milky Way that shouldn't exist. Not because it's impossible, we've proven it's real, but because it challenges everything we thought we knew about gravity, space-time, and the universe itself. It's called Sagittarius A, asterisk pronounced Sagittarius A star, and it's a supermassive black hole. Not just a black hole, supermassive. 4 million times the mass of our Sun, packed into a region smaller than the orbit of Mercury. Imagine taking the entire solar system, all 8 planets, all the asteroids, all the comets, compressing it down to a sphere smaller than Mercury's orbit, and making it so dense that not even light can escape. That's just the start. Here's what will blow your mind. In 2019, scientists at the Event Horizon Telescope collaboration actually photographed Sagittarius A asterisk's shadow. Not the black hole itself. Nothing can escape from inside the event horizon, so we can't see it. But we photographed the glowing material orbiting it and captured the shadow it casts against that radiation. The image that came back was the first direct visual evidence of a black hole, and it was beautiful. A perfect ring of light surrounding absolute darkness. It was haunting. It was real. What makes this mind-bending is how it was captured. They couldn't use a single telescope. No telescope on Earth is powerful enough. So the team coordinated observations from 8 radio telescopes scattered across the globe: Antarctica, Hawaii, Spain, Chile, creating a virtual telescope as large as the entire planet. They synchronized atomic clocks with nanosecond precision and processed data for 2 years to extract the image. Think of it like this: 8 observers standing at different points on Earth, looking at a coin from their positions, comparing notes, and calculating exactly what the coin must look like. Except instead of a coin, it's an object at the center of the galaxy, invisible in normal light, surrounded by the death screams of matter being torn apart and superheated to millions of degrees. And we captured its image. We did that. Humanity did that. Now let's talk about what's actually happening at Sagittarius A*. There's a region called the event horizon, the point of no return. Cross that boundary, and you cannot escape, no matter how fast you're going. Not because it's physically blocked, but because gravity has warped space-time so severely that all possible future paths lead back into the singularity. Einstein predicted this in 1915 when he published General Relativity. He said that massive objects warp the fabric of space-time around them, and gravity is actually just the curvature of space-time itself. Most physicists, including Einstein, thought black holes were mathematical curiosities, interesting on paper, but physically impossible. Nature would prevent them from forming, they reasoned. They were wrong. Nature doesn't give a damn about our comfort level. In 1965, Roger Penrose mathematically proved that black holes were inevitable consequences of general relativity. If gravity was strong enough, if matter was compressed enough, black holes had to form. And in 1974, Stephen Hawking, the same Stephen Hawking who would become one of the most famous scientists of all time, proved something even more shocking. Black holes aren't completely black. They emit radiation due to quantum effects near the event horizon. Think of it like this: at the edge of destruction, at the boundary of forever, quantum mechanics, the laws governing the smallest things in the universe, starts to crack the certainty of general relativity. The laws governing the largest things in the universe. They collide and produce something neither discipline fully understands yet. Here's something that makes Sagittarius A** real. There are stars orbiting it. Not distantly, but actually in orbit around it. One star, called SO-102, completes an orbit around Sagittarius A** every 16 years. Its orbital velocity is somewhere around 5,000 kilometers per second. That's 1.7% the speed of light. For comparison, Earth orbits the Sun at about 30 kilometers per second. SO-102 is moving 166 times faster. It's slingshot whipping around a black hole once per decade and a half. And this isn't theory. Astronomers tracked its position from 1995 onward, calculated its orbit, and in 2020, it completed a full orbit exactly where the equations predicted it would be. We know gravity so precisely that we can predict where a star will be as it orbits a black hole millions of light years away. Let that sink in. The galaxy isn't just orbiting Sagittarius A*. Everything we know is. Our Sun takes 230 million years to complete one orbit. Dinosaurs walked the Earth. The last time our Sun was at the position it occupied when the dinosaurs walked the Earth. When those dinosaurs looked up at the night sky, they saw nearly the same stars we do now, because our solar system has barely moved in the orbital period. Here's the revelation that changes everything. The black hole at the center of our galaxy isn't some aberration. It's a feature. Every large galaxy has one. Apparently, black holes and galaxies grow together. They regulate each other. When a black hole gets too active, it blows out the surrounding gas, preventing new stars from forming. When the gas supply dries up, the black hole quiets down and star formation can resume. Black holes and galaxies aren't opposed to each other, they're dance partners. And Sagittarius A*, far from being destructively active, is actually dormant right now. It's relatively quiet. Imagine the thing we've been afraid of, the monster at the center of our galaxy that could potentially destroy all of spacetime around us, is sleeping. If it woke up, if it became active, if it entered a phase where it was actively consuming material at high rates, it would emit radiation and particles that would dominate the center of the galaxy. It would heat the surrounding gas. It might trigger star formation on a massive scale, or it might shut it down entirely. It would fundamentally alter the structure of our galaxy. But here's the thing that should humble us. This cycle of black hole activity probably shapes galaxies. The existence of galaxies as we know them, with stars, planets, potential for life, might depend on black holes regulating their growth. Our existence might be impossible without Sagittarius ***. This should hit you with an uncomfortable realization. We live in a galaxy. That galaxy is shaped by gravity. That gravity is dominated by a massive black hole at the center. And that black hole's behavior ripples outward, affecting every star, every planet, everything we know. But here's what we haven't even discussed yet. Our galaxy isn't special. It's not unique. What we're about to discover is that the structures we've been examining, the black holes, the stars, the scale, are just a local version of a much larger pattern. In the next section, we're going to zoom out. We're going to leave the Milky Way behind and see where we fit in the larger cosmos. And that's when the real vertigo begins. Imagine you live in a small town. You've spent your entire life understanding your town. You know every street, every person, every building. You think of your town as the whole world. Then one day, you drive to the edge of town and discover there are other towns, not far away, right there. And these other towns exist in relationship to yours. They're in a cluster. They depend on the same supply chains. They share the same culture. You're not isolated. You're part of something larger. That's where we are now. We're about to discover the other towns. Our galaxy, the Milky Way, isn't alone. It exists as part of what astronomers call the local group, a cluster of about 80 galaxies bound together by gravity. 80 galaxies. Not individual stars, galaxies, each one containing billions to hundreds of billions of stars. The local group is dominated by 3 major galaxies. The Milky Way is the largest, or tied for the largest, depending on which recent measurements you believe. The second major galaxy is Andromeda, which is about 2.5 million light-years away. Andromeda might actually be slightly larger than the Milky Way, containing up to 1 trillion stars, compared to our 100 to 400 billion. The third major galaxy is the Triangulum Galaxy, somewhat smaller than both. Here's what will blow your mind. Andromeda is close enough to be visible to the naked eye. On a dark night, away from light pollution, you can see an entire galaxy with 2 trillion stars by just looking up. It's the farthest object visible to the naked eye. When you see it, you're looking 2.5 million years back in time. You're watching light that left Andromeda when your ancestors had just started walking upright on African savannas. Think of it like this. Imagine you're looking at a photograph of your great-great-great-great-grandparent taken millions of generations ago. That's what you're doing when you see Andromeda. You're making contact across incomprehensible distances and incomprehensible timescales. But here's the shocking part. Andromeda is getting closer. It's not moving away like most distant galaxies. It's approaching. In about 4.5 billion years longer than the Sun has left to live, but not by much, Andromeda and the Milky Way will collide. This collision will be catastrophic in scale, but also oddly beautiful. The 2 galaxies won't neatly merge at first. Instead, they'll pass through each other. Gravity will stretch them. Stars will be yanked out of their normal orbits. Some stars will be flung toward the outer regions of the expanding system. Some will be pulled toward the center. The disks will be disrupted. The spiral structures that make galaxies beautiful will be torn apart, and we'll be right in the middle of it. Here's the specific revelation. Our sun is currently in the outer regions of the Milky Way. When the collision happens, the gravitational forces might pull our sun toward the center of the merging galaxy system, or they might fling it to the outer regions, or they might send it in an entirely new direction. The probability of our sun being dramatically displaced is substantial, but the probability of our sun directly colliding with another star in the collision? Incredibly low. Think of it like this. Space is mostly empty. Even in a galactic collision, the chances of stars actually hitting each other is extraordinarily small. It's more like two oceans flowing into each other than two solid objects crashing together. Matter will redistribute. Stars will move. But actual collisions between stars are rare. However, gravitationally, it will be catastrophic. Planets in stable orbits might be jostled out of orbit. Systems will be disrupted. The structure of the resulting merged galaxy will be nothing like either parent galaxy. But wait, the local group itself is moving. It's not stationary. All these galaxies are bound together by gravity, orbiting a common center of mass. But the entire group is moving through space toward a structure called the Great Attractor. The Great Attractor is a gravitational anomaly, a region of space with more mass than can be accounted for by visible galaxies. It's pulling the local group toward it. We're being drawn into a cosmic region of higher density. We don't fully understand why the mass is there. It might be an enormous concentration of dark matter. It might be a region of the universe that just happens to be denser than average. Think of it like this. Imagine the universe as an ocean. Most of it is relatively uniform, but there are currents. And we're being pulled along by a current toward a region of higher density. We're not in control. We're swept along by forces far larger than ourselves. Here's where the perspective shift becomes almost overwhelming. The local group isn't just being pulled randomly. The entire structure of the universe is organized into what astronomers call the cosmic web. Galaxies aren't randomly distributed. They're organized into filaments-long structures of galaxy clusters, separated by vast voids containing almost no galaxies. Imagine the universe as a three-dimensional web. The filaments are made of galaxy clusters. The spaces between are nearly empty, and everything is moving, being pulled by gravity, flowing along the structure of space-time itself. When you see a deep field image from the Hubble Space Telescope, showing thousands of galaxies in a region of sky smaller than a grain of sand held at arm's length, you're seeing structure. You're seeing one tiny corner of the cosmic web. And that pattern repeats everywhere. Filaments and voids, on scales that exceed human comprehension. We are not at the center of this structure. We are not privileged observers. We are embedded in a filament of the cosmic web, riding along on our galaxy in a local group, all of it flowing along the gravitational currents of spacetime toward regions of higher density. And the scale gets worse or better, depending on your perspective. What if I told you that everything we've discussed so far, the Milky Way, with its 100 to 400 billion stars, the local group with its 80 galaxies, the cosmic web with its filaments and voids, what if I told you that all of this is just our local neighborhood? That we've barely started talking about the universe? Here's the fact that should change how you see reality. The observable universe contains approximately 200 billion to 2 trillion galaxies. Not stars, galaxies, each containing billions to hundreds of billions of stars. When we say observable universe, we mean the region of space from which light has had time to reach us since the Big Bang, roughly 13.8 billion years ago. We can't see beyond that because light from more distant regions hasn't had time to travel to us yet. So the observable universe is our cosmic horizon. But it's not the edge of the real universe. It's just the edge of what we can currently know. Let that distinction sink in. We can observe a certain region. The universe extends beyond that. We don't know how far. It might be infinitely large. Let me give you the number that will shatter your sense of scale. In a single cubic megaparsec of space, In volume about 3.26 million light-years on each side, there are approximately 0.1 to 1 galaxies on average. Not a lot of density, but there's that structure. The cosmic web isn't densely packed. Most of space is empty. But take that sparse density and scale it across the observable universe. You get billions and billions of galaxies. When Edwin Hubble discovered that Andromeda was a separate galaxy in 1924, it seemed shocking. We went from one galaxy, or thinking the Milky Way was everything, to two. Today, we know the numbers in the hundreds of billions, possibly trillions. Each discovery made the universe bigger. Each revelation made us smaller. But here's the shocking part. We might still be underestimating. New data from the James Webb Space Telescope, which launched in 2021 and started sending back data in 2022, is showing galaxies in the deep universe that shouldn't exist. We're finding galaxies that are more massive and more mature than models predicted they should be at those early times in cosmic history. This means either our models of galaxy formation are wrong, or we're underestimating the number of galaxies. Or both. Now, let's talk about distance in a way that will make your brain hurt. When you look at a distant galaxy, you're not just looking across space, you're looking back in time. Because light takes time to travel. When we say Andromeda is 2.5 million light-years away, we mean the light we see from Andromeda today left that galaxy 2.5 million years ago. The galaxy we're seeing doesn't exist anymore. Andromeda today, right now, is a different place. It's aged 2.5 million years. It's closer to us. It's already moved. The most distant galaxies we can observe are seen as they were more than 13 billion years ago. We're watching a galaxy that formed when the universe was very young, very different, very strange. The universe in those days wasn't like the universe today. Stars formed at different rates. Galaxies merged more frequently. The cosmic environment was alien? Think of it like this. If you could send a message to a distant galaxy and wait for a response, the round-trip communication would take longer than the entire history of human civilization. You'd send a message, and the answer wouldn't arrive for longer than writing has existed, or agriculture has existed, or civilization has existed. You'd be having a conversation across timescales longer than recorded history. And that's just for the nearest large galaxy. Measuring distance in the universe is extraordinarily difficult. We can't just measure it directly. Instead, astronomers built what's called the cosmic distance ladder, a series of measurement techniques, each one checking and validating the one before it. Edwin Hubble discovered something called Cepheid variable stars that pulse in brightness in a predictable way. The period of pulsing is related to their luminosity. So if you measure how fast they pulse, you can calculate how bright they actually are. Then you measure how bright they appear from Earth. The difference between apparent brightness and actual brightness tells you the distance. Hubble used Cepheid variables in Andromeda to prove it was a separate galaxy. Other astronomers refined the technique. Then they used nearby galaxies' distances to calibrate supernova exploding stars that appear at predictable brightnesses. Then they used supernova to measure the expansion of the universe itself. Each rung on the ladder built confidence in the next. And the ladder revealed an astonishing fact. Not only is the universe vast, but it's expanding. And not just expanding at a constant rate. The expansion is accelerating. In 1998, Saul Perlmutter, Adam Rees, and Brian Schmidt led teams that discovered something that contradicted Einstein himself. They were measuring the expansion rate of the universe using supernova at various distances, tracking the universe's expansion history. They expected to find that the expansion was slowing down due to gravity. They found the opposite. The expansion is speeding up. This discovery meant something was pushing galaxies apart faster than gravity was pulling them together. Gravity wasn't the only force shaping the universe. There was something else, something that acts opposite to gravity, something that permeates all of space. They called it dark energy, and it comprises about 68% of the entire universe. Dark matter makes up about 27%. Ordinary matter stars, planets, you, me, everything we've ever known makes up about 5%. Think of it like this. The universe is a party. Ordinary matter is the people having the party. Dark matter is the building holding the party. Dark energy is the expansion of the building itself, which is accelerating. The people in the building are almost incidental details. The real story of the universe is dark energy pushing everything apart. And we don't know what dark energy is. It's a mystery. It's a placeholder for our ignorance. It's something that makes up 2/3 of the universe, and we don't understand it. Let me give you perspective in a different way. Let's start small and zoom out. You are made of atoms. Atoms are mostly empty space. An atom is a nucleus, a few protons and neutrons, surrounded by a cloud of electrons. The ratio of a nucleus to the size of an atom is roughly the ratio of a marble to a football stadium. An atom is almost entirely nothing. Everything you see, solid matter, rocks, people, planets, is mostly empty space. You are mostly empty space. Now, your body contains about 7 billion atoms. That's a 7 followed by 27 zeros. If you were to think of each atom as a grain of sand, your body would contain more grains than all the beaches and deserts on Earth. But those atoms are organized into a body. The body lives on a planet. The planet orbits a star. The star exists in a galaxy containing 100 to 400 billion other stars. Think of it like this. You are to your body as Earth is to the solar system. A small part of something larger, but still a discrete entity with properties and characteristics. Here's what will break your brain. The sun is so massive that it contains 99.86% of all the mass in the entire solar system. The entire solar system, 8 planets, their moons, the asteroid belt, the Kuiper belt. Everything is dwarfed by a single star. That star is one of billions in our galaxy. Most people have a vague sense that the sun is big and far away. They don't viscerally understand that it is gravitationally dominant. Everything we know, every achievement of human civilization, every person who ever lived, every creature that ever evolved, exists in the gravitational field of a single star, which is, physically speaking, not that large or special. Your sun is a G-type main sequence star. It's sometimes called a yellow dwarf. It's smaller and less luminous than those stars you see in the night sky. The bright stars you see are not typical. They're the rare massive stars that shine so brightly we can see them from far away. The typical star is smaller and dimmer than the sun. Our sun is ordinary, and everything we know depends on an ordinary star's continued existence. Now let's think about Earth's place in this hierarchy. Earth is one of 8 planets in our solar system. It's not the largest. Jupiter is. Jupiter is so massive that you could fit 1,321 Earths inside it. Jupiter is the gravitationally dominant planet in the solar system. It even influences the orbits of the other planets. Earth is the largest terrestrial planet. It's the only one we know of with life. But that's a characteristic of this particular planet, not a characteristic that makes it cosmically important. There are likely trillions of planets in the observable universe. How many host life? We don't know. But the probability that Earth is the only one is infinitesimal. Earth formed about 4.5 billion years ago. It will continue to exist for another 5 billion years or so before the sun expands and engulfs it. In cosmic terms, Earth's habitable zone, the time during which liquid water exists on the surface, might last 7 to 8 billion years total. Life emerged here in under 1 billion years. Humans emerged in the last 300,000 years. Civilization emerged in the last 10,000 years. Writing in the last 5,000 years. Science in the last 500 years. You're living in an astonishing moment. You're living during the era when a planet discovered its own place in the cosmos. Humans went from thinking we were the center of everything to realizing we're a small, temporary phenomenon on a small, temporary planet orbiting an ordinary star in an unremarkable galaxy in an incomprehensibly large universe. Think about what that means. For 95% of human history, we thought Earth was the center of the cosmos. Ptolemy argued that Earth was the center in the 2nd century. That belief lasted over 1,400 years until Copernicus and Galileo challenged it. Even then, it took time to accept it. Once we accepted that we weren't at the center of the solar system, we discovered we weren't at the center of the galaxy. Then we discovered that our galaxy was just one among billions. Then we discovered that the universe might be infinite. Each discovery made us smaller. But here's what philosophers often miss. Each discovery made us more connected. We're not special because we're at the center. We're special because we exist at all. We're made of the same atoms as the stars. We're governed by the same laws of physics. We're part of the universe observing itself. Carl Sagan, the astronomer and science communicator, said something profound. The cosmos is within us. We are made of star stuff. We are a way for the cosmos to know itself. Every atom in your body, heavier than hydrogen, was created in a star's furnace. The carbon in your DNA, the calcium in your bones, the iron in your blood, all forged in stars. When those stars died, they scattered those atoms across space. Those atoms formed part of a nebula. That nebula collapsed into our solar system. Those atoms became Earth. And those atoms became you. You are not separate from the cosmos. You are a manifestation of it. The universe became conscious through you. Now think about time. The universe is 13.8 billion years old. The Milky Way formed about 13.6 billion years ago. Life on Earth emerged about 3.8 billion years ago. Humans emerged about 300,000 years ago. Civilization emerged about 10,000 years ago. You are living in the 21st century. If you live to 80 years, you will have experienced about 0.0000003% of the time since the universe began. You will have experienced 0.000000001% of the time since the Milky Way formed. But in those tiny sliver of time, you are aware. You are conscious. You are thinking about your place in the cosmos. That's extraordinary. Now that we've zoomed out and then back in, let's get specific about where the Milky Way sits in the galactic hierarchy. We've established that the Milky Way is one of 3 dominant galaxies in the local group. But how does it stack up against the universe at large? The Milky Way is large. With 100 to 400 billion stars, it's bigger than most galaxies. But there are bigger ones. IC 1101 is an ultraluminous infrared galaxy. It might contain 100 trillion stars. That's 250 times more stars than our highest estimate for the Milky Way. Imagine a galaxy where our entire galaxy is a small neighborhood. The Milky Way is old. It formed about 13.6 billion years ago when the universe was very young. The stars in the bulge at its center are nearly as old as the universe itself. The disk stars are somewhat younger, formed from material enriched by earlier generations of stars. Think of it like this. The Milky Way is middle-aged. It's had time to develop its current structure and complexity, but it's not ancient, and it still has a long future ahead. Here's something that blew my mind when I first learned it. The spiral arms of the Milky Way aren't solid structures. They're not like grooves in a record. They're density waves. They're regions where the galactic disk is slightly denser than average. Stars move through them like traffic moving through congestion on a highway. Our sun is currently in the Orion Arm, a minor spiral structure. It passes through spiral arms roughly every 100 million years or so. When it passes through them, the density increases, the radiation environment changes, the cosmic ray flux might change. Some scientists have speculated that these passages might correlate with extinction events on Earth, though the evidence is mixed. But here's what's genuinely mind-bending. The spiral structure rotates more slowly than the stars. This creates what's called the density wave. Stars orbit the galactic center once every 230 million years. The spiral arms rotate once every 600 million to a billion years, depending on which spiral structure you're measuring. Think of it like this. Imagine cars on a highway moving faster than the traffic waves. A car passes through a congested area, moves into clear road, and then encounters congestion again as it catches up with the next wave. That's how the spiral arms work. They're not physical structures that stars follow. They're patterns that stars flow through. We tend to think of the Milky Way as the disk, the beautiful spiral structure that dominates the visible light. But the disk is embedded in something far larger, the galactic halo. This is a spherical region of space surrounding the disk, extending far beyond it, filled with globular clusters and dark matter. The galactic halo extends out to hundreds of thousands of light years. It contains the oldest stars in the galaxy. It's where the streams of stars torn from smaller satellite galaxies are being incorporated into the Milky Way. It's where the subtle gravitational signatures of the collision with Sagittarius dwarf elliptical galaxy show up. And it's mostly dark matter, invisible, gravitationally controlling, determining how the galaxy rotates, how it moves, how it interacts with other galaxies. Think of it like this. The visible galaxy is like the sun. The halo is like the solar wind, mostly invisible, but vastly more expansive and equally important to the overall system. One of the greatest discoveries of recent years has been the mapping of the Magellanic Stream, a trail of gas stretching from the Magellanic Clouds toward the Milky Way. The Magellanic Clouds are two dwarf galaxies orbiting the Milky Way. They're in the process of being torn apart by tidal forces. The Magellanic Stream is material that's being stripped from these galaxies and pulled toward the Milky Way. It's a structure that spans hundreds of thousands of light years. It's evidence of the Milky Way actively cannibalizing smaller galaxies. It's evidence of cosmic violence on a scale we're only beginning to map. This isn't theory. We can detect the gas in the stream. We can see where it's coming from and where it's going. We can understand the timescale of the interaction. And it's telling us something profound. Galaxies don't exist in isolation. They interact, they merge, they consume and are consumed. The Milky Way will eventually consume the Magellanic Clouds. Some of their material is already flowing toward us. The process is slow cosmically speaking. It's happening quickly, but in terms of human perception, it's imperceptibly gradual. But it's happening. The Milky Way has about 50 confirmed satellite galaxies, smaller galaxies bound by gravity and orbiting our galaxy. The two largest are the Large and Small Magellanic Clouds. But there are dozens of others, mostly dwarf galaxies, barely visible even with large telescopes. As these satellite galaxies orbit, they're gradually being torn apart. Their gravity is too weak to maintain cohesion against the tidal forces of the Milky Way. Their stars are being stripped away and incorporated into the Milky Way's halo. Streams and trails of stars mark the orbits of these destroyed galaxies. Our galaxy is a cosmic predator, slowly consuming its satellites. And it will eventually be consumed itself by Andromeda. This is the cycle. Galaxies merge. Smaller ones are eaten by larger ones. The universe is not static. It's dynamic. It's violent. It's constantly reshaping itself. Here's a question that astronomers have been grappling with for decades. If galaxies form from the same primordial conditions as the Big Bang, why do they have such different structures? Some are spiral, some are elliptical, some are irregular. Some are so massive they contain trillions of stars. Some are so small they contain only 1 million. The answer involves dark matter, collisions, gas cooling, and star formation rates. It involves the initial angular momentum imparted by quantum fluctuations in the early universe. It involves the history of mergers and interactions. No galaxy's structure is simple. Every galaxy is a record of its collisions and interactions and evolution over billions of years. The Milky Way's structure tells a story. It has a bulge of old stars at the center. It has a disk of younger stars rotating in the plane. It has satellite galaxies in the process of being consumed. It has a halo of dark matter. It has streams of stars from past mergers. It has regions of active star formation and regions of inactivity. When you look at the Milky Way, you're looking at a galaxy that's had a complex history and is actively evolving. Here's a discovery that changed how we think about galaxies. The bulge at the center of the Milky Way isn't just a bulge. It's also a bar. The Milky Way is a barred spiral galaxy. That bar elongated structure extending from the center affects how gas flows in the galaxy, how star formation is distributed, and how the gravitational field is organized. We didn't even know our galaxy was barred until the early 2000s. We were inside it. We couldn't see the structure. It took infrared observations that could penetrate the dust in the galactic plane to reveal it. Think of that. We live inside the Milky Way. We've studied it for thousands of years. We've built the most sophisticated telescopes ever created. And only recently, we discovered a major structural feature we didn't even know existed. And that's probably not the last surprise. As we develop new telescopes and new ways to observe, we'll probably discover more about our galaxy that we didn't even know we were missing. The Milky Way isn't uniformly populated with stars. Star formation happens in regions. In the molecular cloud's dense regions of gas and dust, new stars are being born continuously. In regions like the Orion Nebula, we can see star formation happening. Gravity is pulling gas together, creating hot, dense cores that ignite fusion. Disks of material surrounding forming stars become planetary systems. Some stars are born in clusters of thousands of stars, all formed from the same molecular cloud, all roughly the same age. The Milky Way is birthplace of stars and systems. Every day, somewhere in our galaxy, new stars are forming. New planets are accreting. New potential homes for life are being created. At the same time, other stars are dying. Red giants are swallowing their planets. Neutron stars and black holes are collapsing space around them. The galactic environment is dynamic. It's violent. It's creating and destroying continuously. Think of it like this. The Milky Way is not a stable museum. It's an alive ecosystem where matter cycles from stellar furnaces to planetary atmospheres to the surfaces of planets and back again. Life is embedded in this cycle. Massive stars that explode as supernovae create cosmic rays, high-energy particles that zip through space at nearly the speed of light. These cosmic rays interact with the interstellar medium. They excite electrons. They create secondary particles. They propagate through the galaxy. Some of these cosmic rays reach Earth. We're bathed in them constantly. They create interesting isotopes as they hit our atmosphere. They potentially drive cloud formation and affect climate. They're a constant source of radiation that we evolved with and our bodies have adapted to. But here's what's mind-bending. These cosmic rays originated in supernova billions of light years away. They've been traveling through space, crossing the Milky Way for millions or billions of years. When they hit Earth, they're ghosts of distant stellar catastrophes. We're not isolated. The universe is constantly interacting with us through these streams of particles. We're embedded in the cosmic weather of the galaxy. The Milky Way has a magnetic field. It's not as strong as Earth's magnetic field, but it exists on a galactic scale. It's shaped by the rotation of the galaxy and the movement of charged particles. It has structure. It has regions where it's stronger and weaker. This magnetic field is real. It's not just theoretical. We can detect it by observing polarized radiation from distant sources and seeing how the polarization is affected by the magnetic field. We can map its structure. We can understand how it evolves, and it affects what happens in the galaxy. Magnetic fields affect how gases move. They affect where star formation can occur. They affect how jets from black holes propagate. They're a fundamental part of galactic structure. The universe is electric. The universe is magnetic. The Milky Way is not an isolated system floating in empty space. It's embedded in fields of force. It's connected to the cosmic environment around it through radiation, particles, and fields. By now, you've heard a lot of numbers, big numbers, incomprehensibly big numbers, billions of stars, millions of light years, billions of years of time. Your brain might be numb to them. But I want to take a moment to talk about why understanding these scales matters. When you truly grasp the scale of the Milky Way, something shifts in your consciousness. You realize that your problems, while they may feel overwhelming, exist on a microscopic scale compared to the cosmos. You realize that your achievements, while they may feel significant, are local phenomena in a vast, indifferent universe. That might sound depressing, but it's not. It's liberating. If the cosmos is incomprehensibly vast, then your suffering is also temporary and small. If your accomplishments are insignificant on a cosmic scale, then so are your failures. You are free from the tyranny of cosmic significance because the cosmos doesn't care. But here's what's profound. The cosmos cares that you exist at all. The universe, through the process of evolution over billions of years, has created a being capable of understanding itself. You, right now. Thinking about the scale of the Milky Way. That's extraordinary. Let me hit you with a perspective shift that might change how you see this whole discussion. Everything we've said about the Milky Way being large, being vast, being incomprehensibly scaled, that's true. But it's also parochial. Here's what the latest science is showing us. The Milky Way might be larger than we think in ways that can't be easily captured by simple measurements. When we measure the Milky Way by visible stars, we get to about 200,000 light years across. But the dark matter halo extends further. And if you include the extended stellar halo and the streams of stars being incorporated into the galaxy, the structure might extend to nearly 1 million light years. And that's just the gravitationally bound system. Beyond that, the universe continues infinitely or near infinitely, filled with billions upon billions of other galaxies, each with their own scales and structures and complexities. We've been trying to zoom out, but the universe doesn't have a zoom limit. What strikes me most about understanding the Milky Way scale is how recent this understanding is. For most of human history, we thought the Milky Way was the entire universe. We thought we were at the center. We thought the cosmos was fundamentally small and comprehensible. In the last 100 years in Evelink in cosmic terms, we've gone from that view too, understanding that we live in a galaxy among billions, in a universe that might be infinite, governed by forces we still don't fully comprehend. This is astonishing intellectual progress, and it's driven by curiosity. Pure, relentless curiosity. People asking questions. People looking up at the sky and wondering. People building better tools to see further. People developing theories to explain what they see. You're living in an era of unprecedented cosmic awareness. Your ancestors could look up and see stars, but not understand what they were. Your descendants might understand far more than you do. But you're here, now at this moment, able to grasp the scale of the universe in a way that was literally impossible just centuries ago. Understanding the scale of the Milky Way raises profound questions. If our galaxy contains hundreds of billions of stars, and a significant percentage of stars have planets, and a percentage of those planets might have habitable conditions, then how many potential homes for life exist in just our galaxy? Current estimates suggest billions, possibly tens of billions, possibly hundreds of billions. We don't know. We've only detected a few thousand exoplanets so far, and we're finding them extremely common. If even a small percentage of habitable planets develop life, then life exists in vast abundance in the Milky Way. And the Milky Way is just one of perhaps 200 billion to 2 trillion galaxies. Do you see the implication? Either we are extraordinarily fortunate to have civilization emerge on our planet, in our corner of the galaxy. Or we're statistically unremarkable, and civilization emerges frequently throughout the cosmos. This is the Fermi paradox. If life is common, where is everybody? Why haven't we detected signals from alien civilizations? Why haven't we been visited? Why are we alone? There are many answers to these questions. Maybe life is rarer than we think. Maybe intelligent life is even rarer. Maybe civilization is self-limiting. Perhaps advanced civilizations always destroy themselves before becoming spacefaring. Maybe life does exist out there, but we're too far away to contact, separated by distances that communication and travel can't bridge, at least not easily. Or maybe we're wrong about something fundamental. Maybe our assumptions are off. Maybe we're not understanding something about how physics works, or how life emerges, or how intelligence develops. But here's what the scale of the Milky Way tells us. Whether or not we ever make contact with other civilizations, we are not alone in being part of something vast. We are part of a galaxy containing hundreds of billions of stars. We are part of a universe containing billions of galaxies. We are part of a cosmos that, as far as we can tell, is governed by consistent, comprehensible laws. That should give us hope. It means the universe is not magical or arbitrary. It means understanding is possible. It means science works. It means we can keep learning and keep discovering and keep pushing the boundaries of our knowledge. But it should also give us concern. If we are among billions of stars, if our world is fragile and finite, if cosmic catastrophes are possible, then we should take seriously our responsibility to preserve what we have. We should recognize that Earth, however common planets might be in the universe, is precious. It's our home. It contains the only life we know of. It contains human civilization with all our art, music, science, and culture. The scale of the Milky Way is humbling, but it should humble us into action, not into despair. Before we go further, let's talk about how we even know all this. How do we know the size of the Milky Way when we're embedded inside it? How do we know about dark matter when we can't see it? How do we measure distances to galaxies billions of light years away? The answer is that scientists have developed increasingly sophisticated tools and methods. It started with the naked eye, then Galileo's telescope, and bigger telescopes. Now we have space-based telescopes like Hubble and James Webb, which can see deeper and further than anything on Earth's surface. The Hubble Space Telescope, launched in 1990, revolutionized our understanding of the universe. It could see objects billions of light years away. It could measure the distances to galaxies. It could reveal the expansion rate of the universe. It changed everything. In December 2021, the James Webb Space Telescope launched. It's more powerful than Hubble in many ways. It observes in infrared wavelengths, allowing it to see through dust that would block visible light. It can see the earliest galaxies, formed when the universe was just a few 100 million years old. It's revealing surprises about how quickly galaxies formed and how large the earliest galaxies were. These telescopes are our eyes extended into the cosmos. Through them, we're learning that our assumptions were often wrong. Here's something that should shake your understanding of what we know. The universe we see now is not the universe as it exists now. We are seeing the past. The light from the most distant galaxies took billions of years to reach us. In that time, the universe has changed, the galaxies have moved. Some have merged, some have formed new stars. Some have shut down star formation entirely. When we look at the Hubble Deep Field, a tiny region of sky photographed in 1995, showing thousands of galaxies, we're not looking at what those galaxies are like today. We're looking at what they were like when they were young. It's a time capsule. It's archaeology of the universe. And here's what breaks minds. The universe is expanding. The distant galaxies are not just far away. They're getting farther away. Their light is being stretched as it travels toward us. This stretching is called redshift. By measuring how much the light is shifted toward the red end of the spectrum, we can determine how fast the galaxy is moving away from us. We're not just observing the universe. We're watching it expand in real time through light that's been traveling toward us for billions of years. The James Webb Space Telescope is just the beginning. Astronomers are planning even larger telescopes. The extremely large telescope being built in Chile will be about 39 meters across. The Giant Magellan Telescope will be about 25 meters. These will be more powerful than anything we have now. They'll be able to see even further back in time. They'll be able to study the atmospheres of exoplanets to search for signs of life. They'll be able to map out the structure of galaxies in unprecedented detail. They might discover phenomena we haven't even thought to look for. And that's on Earth. In space, new missions are being planned. A successor to the James Webb Space Telescope is already in early planning stages. Missions to search for biosignatures in exoplanet atmospheres. Missions to study the first galaxies and the earliest stars. The future of astronomy is going to be even more revelatory than the past. We haven't even started to understand the universe. We've barely figured out how to ask the right questions. One of the most profound questions we can ask is, are there other worlds like Earth? Are there planets where life might exist? Current methods allow us to detect exoplanets by watching them pass in front of their stars, looking for the slight dimming of light. We can measure the planet's mass by watching how it gravitationally affects its star. We can estimate the planet's temperature based on its distance from its star. We found thousands of exoplanets, and we're finding that planets are extremely common. Most stars have at least one planet. Some have dozens. The universe is teeming with worlds. Many of these worlds are in the habitable zone, the region around a star where temperatures allow liquid water to exist. We don't know if these worlds have life. We don't know if they have atmospheres, but they exist. They're real. They're out there. And as telescopes get more powerful, we'll be able to study these worlds in more detail. We'll be able to measure their atmospheric composition. We'll be able to look for signs of life biosignatures. We might, within the next few decades, discover whether we're alone. This brings us back to the question that haunts us. Are we alone? The Milky Way contains hundreds of billions of stars. A significant fraction have planets. A percentage of those planets might have conditions suitable for life. If even 1 in a million planets develops life, that's hundreds of millions of worlds with life in our galaxy alone. If even 1 in a billion planets develops intelligent life, that's still hundreds of thousands of civilizations in our galaxy alone. But we see no sign of them. No signals, no visitors, no artifacts, silence. This silence is profound. It demands explanation. Either we're alone, which seems statistically unlikely, or we're wrong about something. Maybe intelligent civilizations are rare. Maybe they're self-limiting. Maybe they're far away. Maybe they're hiding. Maybe communication across cosmic distances is harder than we think. But it's also possible that we're on the cusp of discovery. Maybe, within our lifetime, we'll detect a signal from an alien civilization. Maybe we'll find microbial life on an exoplanet. Maybe we'll realize that life is far more common than we thought. And maybe, just maybe, we'll discover that we're not as alone as we feel. Let me bring this back to something personal. Where did you come from? Your atoms came from stars. Billions of years ago, the first stars formed from primordial hydrogen and helium. These massive stars fused elements in their cores. When they died, they scattered those elements across space. New stars formed from that enriched material. This process repeated. Each generation of stars produced heavier elements. Carbon, nitrogen, oxygen, silicon, iron, all the heavy elements that would eventually make up planets and life. The universe was slowly enriching itself with complexity. About 4.6 billion years ago, in a region of the Milky Way, a star died. It exploded as a supernova. Its shock wave compressed a nearby gas cloud. That cloud began to collapse under its own gravity. It rotated. It flattened into a disk. A new star formed at the center of our sun. Planets formed in the disk. The iron and nickel that fell to Earth and formed its core came from that stellar explosion. The oxygen you breathe, the carbon in your DNA, the calcium in your bones, all created in stellar furnaces, forged in stars, scattered across space, incorporated into planets, incorporated into you. Think of it like this. You are made of stardust, not metaphorically, literally. Atoms that were created in a star are now arranged in your brain, allowing you to think about your cosmic origins. That's not poetic license. That's chemistry. Life emerged on Earth about 3.8 billion years ago. We don't know exactly how. It might have emerged in hydrothermal vents at the ocean floor. It might have emerged in warm, shallow pools. It might have been delivered from space on meteorites. But it emerged. The first life was simple. Single cells, no nucleus, no mitochondria. Just a membrane containing genetic material and some proteins. But those simple cells had the ability to replicate, to evolve, to compete. Over billions of years, life became more complex. Photosynthesis emerged, allowing organisms to use the sun's energy directly. Oxygen accumulated in the atmosphere, creating new opportunities for life. Multicellular organisms evolved. Plants and animals diversified. Life became more complex, more competitive, more remarkable. Humans emerged only recently. Our species, Homo sapiens, emerged about 300,000 years ago. We're a young species. We're a new experiment in consciousness and intelligence. We're babies in cosmic terms. But in our short existence, we've done something remarkable. We've become conscious of our own cosmic origins. We've figured out how atoms are created in stars. We've measured the expansion of the universe. We've understood the laws of physics. We've become aware of our place in the cosmos. And here's the revelation that should shatter how you see yourself. The universe is aware of itself through you. The cosmos doesn't have eyes, except for the eyes we create. It doesn't have a mind, except for minds like ours. It doesn't ask questions, except the questions we ask. For 13.8 billion years, the universe existed without self-awareness. Matter formed, stars ignited, galaxies formed. But there was no perspective from within to observe it. Then, on one small planet, around one ordinary star, in one unremarkable galaxy, consciousness emerged. And suddenly, the universe could observe itself. You're not separate from the universe. You're part of it. You're the universe's way of becoming conscious. Every time you learn something about the cosmos, you're the cosmos learning about itself. Every time you ask a question about reality, reality is asking a question through you. That's profound. That's humbling. That's extraordinary. Understanding this brings responsibility. If we are the universe aware of itself, then we have a duty to preserve that awareness. We have a duty to keep learning, keep discovering, keep pushing the boundaries of our knowledge. But we also have a duty to each other. If we're all made of the same stardust, if we're all part of the same cosmic story, if we're all expressions of the same physical laws, then we're fundamentally connected. Your atoms were forged in different stars than mine, but we're both made of stardust. We're both part of the same universe. We're all in this together. This cosmic perspective should make us more compassionate, not less. If we're all insignificant on a cosmic scale, then our local suffering matters more. If we're all temporary, then our time together matters more. If we're all part of something vast, then we should care for each other and the world that sustains us. The Milky Way has been around for 13.6 billion years. It will continue to exist for trillions of years into the future. Our sun has 5 billion years left before it dies. Humanity has existed for less than 1 million years. Civilization has existed for 10,000 years. We're not guaranteed a future. We're not guaranteed that our species will survive. We're not guaranteed that our civilization will continue. But if we choose to, if we work together, if we take seriously our role as conscious observers of the universe, we could last for millions of years. We could spread beyond Earth. We could become a spacefaring civilization. We could send our consciousness out into the cosmos. But first, we have to survive. We have to overcome the challenges we face on this planet. We have to build a civilization that values knowledge, values compassion, values the continuation of consciousness in the universe. This understanding of our place in the cosmos should motivate you, not to despair about your insignificance, but to be inspired by your connection to something vast. You're made of stardust. You're part of a galaxy with hundreds of billions of stars. You're conscious. You're aware. You can understand the universe. That's power. That's capability. That's responsibility. Look at the stars tonight and remember, you're not looking at something separate from you. You're looking at your origins. You're looking at the rest of your family. You're looking at the cosmos that made you and continues to sustain you. And if you ever feel small, remember that smallness is the gift. In being small, you're free. In being temporary, you're precious. In being part of something vast, you're connected to everything. Let's talk about what's going to happen to our galaxy. Not tomorrow or next year, but on cosmic timescales. What does the future hold for the Milky Way? We already know some major events. In about 4.5 billion years, Andromeda will begin to collide with the Milky Way. The two galaxies will pass through each other. Stars will be ejected. Gas will be heated. The structure of both galaxies will be destroyed. The result will be a new galaxy formed from the two. What will the merged galaxy look like? We don't know exactly. Simulations suggest it might be a large elliptical galaxy. It might be chaotic and turbulent during the merger, with active star formation triggered by the collision. Over billions of years, it might settle into a new equilibrium. This merged galaxy, sometimes called Milkomeda or Miltromida, will be the dominant large galaxy in the local group. The other smaller galaxies will continue to be consumed. Eventually, the local group will merge into a single large galaxy, or possibly a few dominant galaxies orbiting a common center. But even the local group is not the final level. The local group itself is part of the Virgo supercluster, a larger structure of galaxy clusters stretching across billions of light years. And the Virgo supercluster is part of the Laniakea supercluster, a structure so vast we only discovered it in 2014. These superclusters are bound together by gravity, but they're also moving. The local group is moving toward the Great Attractor. We don't fully understand why. It might be due to massive concentrations of dark matter beyond our direct observation. On timescales of billions of years, galaxy clusters will continue to merge. The structure of the universe will continue to organize itself through gravity into larger and larger structures. Eventually, the universe might reach an equilibrium, or it might continue expanding forever, with gravity never fully organizing all the matter. Here's what will blow your mind about the far future. In about 100 billion years, all the stars we can see from Earth, all the galaxies visible in the current universe, will be gone beyond the horizon. The universe will have expanded so much that the light from distant galaxies will be permanently out of reach, even traveling at the speed of light. A civilization existing 100 billion years in the future, looking up at the sky, wouldn't see the billions of galaxies we see now. They'd see a nearly empty universe. Just their own local cluster of galaxies, and maybe a few nearby clusters. The rest would be forever beyond observation. This is called the cosmic horizon. Due to the expansion of the universe, there's a distance beyond which light will never reach us. And due to expansion, that distance is shrinking. Galaxies are disappearing beyond the horizon as we watch. In 1 trillion years, most of the universe will be unreachable, unobservable, inaccessible. A civilization in the far future might come to the wrong conclusion. They might think the universe is small. They might think they're alone. They might not realize there are billions of galaxies beyond their horizon, having been left behind by the expansion of space itself. But before we get to that distant future, the Milky Way will go through a dramatic transformation. Stars will slowly die. Massive stars will explode. Smaller stars will gradually use up their nuclear fuel and cool into white dwarfs and brown dwarfs. In about 10 billion years, the Milky Way and all galaxies will have formed most of its stars. The age of star formation will be declining. Galaxies will become darker as existing stars age and dim. New planets won't form. Life in the galaxy will become harder to sustain. In about 100 billion years, star formation in most galaxies will be essentially complete. No new stars will be born. Existing stars will slowly die. The universe will become a dark place, populated by cold, dead stellar remnants and planets without stars. But here's what's remarkable. Some stars will live nearly forever. The smallest, coldest red dwarf stars might last for 100 trillion years, or more, much longer than the current age of the universe. A civilization that exists trillions of years in the future, orbiting a red dwarf, could still have a source of energy and heat. This raises a profound question. Could a civilization last forever? Could consciousness, once emerged in the universe, persist indefinitely? Some physicists and philosophers have speculated about this. If a civilization is clever enough, if they can harness the energy of stars efficiently, if they can move when their star dies, they could potentially persist for as long as stars exist. They could colonize galaxies. They could survive the merger of the Milky Way and Andromeda. They could potentially exist until the last stars die. But eventually, in about 10,100 years, a number so large it doesn't have a name, called a Google, the last stars will die. The universe will become cold and dark. There will be no more energy to harness. Consciousness, if it still exists, would have to find new ways to sustain itself. Some have speculated about far future civilizations uploading their consciousness into digital substrates, running on the tiny amounts of energy available from matter decay or Hawking radiation from black holes. Others have proposed that intelligence might become diffuse, taking advantage of quantum effects to achieve computation with minimal energy. It's speculative. It's far future. But the point is, consciousness is fragile. It depends on energy. It depends on the physical structure of the universe. The long-term future of consciousness depends on the laws of physics and how the universe evolves. Understanding this long-term future brings us back to responsibility. We exist now. We have a brief window, a few billion years, before our sun becomes uninhabitable, a few trillion years before the stars run out. If consciousness is to persist in the universe, if self-awareness and knowledge are to continue beyond the present age, then we have a responsibility to make sure it happens. We have a responsibility to preserve life on Earth, to develop technology that allows life to spread beyond Earth, to create a civilization resilient enough to survive cosmic catastrophes. We have a responsibility to the future, not just the future of humanity, but the future of consciousness in the universe. We might be one of the first conscious species in the universe. We might have a role to play in ensuring that consciousness continues. That's a profound responsibility, and it comes from understanding our place in the cosmos. At this point, if you've stayed with me this entire journey, your brain is probably oscillating between wonder and a kind of existential vertigo. You're thinking about numbers too large to visualize. You're contemplating your own insignificance. You're realizing that you live on a small planet, orbiting an ordinary star in a galaxy among billions in an apparently infinite universe. This is the moment where most people experience something called the overview effect, a cognitive shift that occurs when a person sees their place in the cosmos from a new perspective. It's a combination of awe, insignificance, and connection. Astronauts who've seen Earth from space often report this effect. They look down at the planet and see it as a single integrated system, precious and fragile, isolated in the void. They see national borders. From space they disappear. They see the thinness of the atmosphere. It's just a thin line. They feel profound humility and profound connection at the same time. You don't need to go to space to experience the overview effect. You can experience it by truly understanding your place in the cosmos, by visualizing the scale of the Milky Way, by comprehending that you're made of stardust, orbiting a black hole in a galaxy among billions, in a universe that might be infinite. But here's what's important. Just because you're small in cosmic terms doesn't mean you're insignificant. This is a paradox that we need to grapple with. You are made of atoms forged in stars. Your consciousness is an emergent property of matter organized in a particular way. The laws of physics that govern stars also govern your body. The same chemistry that creates planets also creates your molecules. You are not separate from the cosmos. You are a localized manifestation of it. You are the universe experiencing itself. When you think, when you feel, when you love, when you create, the cosmos is thinking, feeling, loving, and creating through you. In a very real sense, the Milky Way is aware of itself through your consciousness. If you died tomorrow, the Milky Way would continue, but something precious would be lost. A particular perspective, a particular consciousness, a particular expression of the universe's attempt to understand itself would be gone. That's significant. That matters. Here's the revelation that should reshape how you see yourself. The universe didn't create you by accident. I'm not talking about divine creation or predetermined destiny. I'm talking about probability and physics. For you to exist, an incredibly precise sequence of events had to occur. Your parents had to meet at the right moment. Your particular combination of genetic material had to form. Your particular neural connections had to develop. Your particular experiences had to shape your consciousness. The probability of all of this is so low that it's effectively zero. If the universe were slightly different, if any major event were slightly altered, you wouldn't exist. This doesn't mean you are destined to exist. It means you're impossibly fortunate to exist at all. You shouldn't exist, and yet you do. And you're here, at this moment in cosmic history, capable of understanding the universe that created you. That's not an accident. That's the universe achieving something extraordinary. This understanding brings a moral weight. If consciousness is rare and precious, if you exist against impossible odds, then your consciousness has value. Not cosmic value. The universe doesn't care about your preferences, but real meaningful value. Your experiences matter, not because the universe cares about them, but because they're the only experiences you have. Your time is limited. Your time on this planet is shorter. Your time in existence is finite. Given that finitude, how do you want to spend your time? What kind of consciousness do you want to be? What kind of impact do you want to have? These questions have no cosmic answers. The universe doesn't tell you how to live. Physics doesn't prescribe morality. But biology, evolution, and conscience suggest that consciousness naturally cares about other consciousness. We're wired to care about each other. We're wired to build communities, to cooperate, to create meaning together. Understanding the scale of the Milky Way should make you appreciate your local community more, not less. If you're insignificant on a cosmic scale, then what matters is the relationships you have, the people you love, the community you're part of. The local is precious precisely because the cosmic is vast. Psychologists have studied what happens to people when they have experiences of awe, when they encounter something so vast that it exceeds their sense of scale. And they found something remarkable. People who experience awe become more generous, more compassionate, more connected to others. Understanding the scale of the Milky Way is designed to trigger awe. And that awe should make you a better person. It should make you more generous to others. It should make you recognize your common ground with every other human, every other conscious being, every manifestation of the universe's attempt to understand itself. If that sounds manipulative, using cosmic perspective to engineer compassion, I'd argue it's not manipulation. It's truth. If you're all made of stardust, if you're all part of the same cosmic system, then you are connected. Recognizing that connection isn't being tricked. It's being honest about reality. But we need balance. We need to hold two truths simultaneously. You are insignificant on a cosmic scale, and you are precious and significant in your local context. The Milky Way is so vast that it doesn't care about you. It will exist for trillions of years after you're gone. Your actions won't change the fate of galaxies or the structure of space-time. But your actions will change the world of the people around you. Your kindness will matter to someone. Your knowledge will matter to someone. Your presence will matter to someone. The goal isn't to use cosmic perspective to devalue the local. It's to use cosmic perspective to reframe the local as precious, despite being insignificant on cosmic scales. You are insignificant and precious. These aren't contradictions. They're the two truths you need to hold to live a meaningful life. We started with a shock. We're moving through space at incomprehensible velocity, and it would take our fastest spacecraft 230 million years to cross our galaxy. We've journeyed from that revelation through the structure of the Milky Way, through its place in the cosmos, through the implications for our own existence. We've talked about Edwin Hubble discovering separate galaxies. We've talked about Vera Rubin finding evidence of dark matter. We've talked about Saul Perlmutter, Adam Rees, and Brian Schmidt discovering that the universe's expansion is accelerating. We've learned that the sun is ordinary, that Earth is not special except for having us on it, that humanity is recent and fragile, that consciousness is improbable and precious. We've talked about the future, about Andromeda colliding with the Milky Way, about superclusters merging, about the eventual cooling and darkness of the universe billions of years hence. We've talked about your place in this cosmos made of atoms forged in stars, conscious in a way that makes the universe aware of itself, precious despite being insignificant on cosmic scales. But I'd be remiss if I didn't acknowledge the limits of our knowledge. We've talked about things we know with confidence, the size of the galaxy, the distance to nearby galaxies, the age of the universe. But we've also touched on mysteries we don't understand. We don't know what dark matter is. We don't know what dark energy is. We don't know if there are other universes beyond our observable universe. We don't know if the laws of physics are universal or local. We don't know if consciousness is unique to biological systems or if it can emerge in other substrates. We don't know if we're alone. We don't know how often life emerges. We don't know how often intelligent life develops. We don't know if civilizations typically survive their technological adolescence. We know a lot, but we know more about what we don't know than about what we do. And here's the revelation that should leave you in awe. We're only getting started. Humanity has been asking cosmological questions for only a few thousand years. We've had telescopes for 400 years. We've had space-based telescopes for 30 years. We've been analyzing the universe with computers for maybe 50 years. We're infants. We're babies in cosmic terms, and we're only just beginning to understand the universe. In the next century, we'll probably discover things that reshape our understanding as dramatically as Hubble's discovery of other galaxies. We might detect signs of alien life. We might discover new laws of physics. We might find that our universe is part of a larger multiverse. We might develop technology that allows us to explore the galaxy. You're living at the threshold of discovery. You're living at a moment when humanity is on the cusp of understanding its place in the cosmos, and you have the opportunity to contribute to that understanding. I've asked you to think about your place in the Milky Way. I've asked you to contemplate the scale of the galaxy and the universe. I've asked you to understand yourself as made of stardust, as conscious, as precious. But I'm not asking you to do this passively. I'm asking you to do something with this understanding. I'm asking you to participate in the cosmic story. You don't need to be a professional astronomer. You don't need to dedicate your life to science. But you can take this understanding and let it change you. You can look at the stars and feel the awe. You can recognize your connection to others. You can let cosmic perspective make you more compassionate, more curious, more humble. You can teach others. You can share this understanding with your friends, your family, your children. You can be part of the great project of consciousness understanding itself. You can pursue your curiosity. If questions arise about the universe, about existence, about meaning, you can investigate them. You can read. You can learn. You can wonder. You can push the boundaries of your knowledge. You can take seriously your role in the cosmic story. You're not just living on a planet. You're part of the universe's process of self-understanding. That's profound. That's sacred. That's worth dedicating yourself to. The Milky Way is 13.6 billion years old. It will continue for trillions of years more. But humanity has existed for only 300,000 years. Civilization for 10,000 years. You, as an individual, for a brief moment. In that brief moment, you have the opportunity to understand something profound. You have the opportunity to know your place in the cosmos. You have the opportunity to be conscious in a universe that was unconscious for billions of years. Don't waste that. Don't take it for granted. Don't assume that understanding the cosmos is unnecessary or abstract. It's the most practical, the most important, the most transformative knowledge you can have. Because understanding your place in the cosmos changes how you see everything. It changes how you treat other people. It changes your priorities. It changes what you value. And that change propagates. If enough people understand their place in the cosmos, if enough people feel the awe and the connection and the responsibility, we could create a civilization that's different, better, more compassionate, more curious, more dedicated to understanding and preserving consciousness. I want to leave you with one final revelation. It's a synthesis of everything we've discussed, brought down to a personal level. You are not alone. Not because aliens are out there, they might be, but that's not the point. You're not alone because you're connected to every other conscious being through the cosmos that created you both. You're not alone because every atom in your body was forged in a star and scattered across space. You're not alone because the light from distant galaxies that we've discussed throughout this video will eventually reach you, teaching you about the universe. You're not alone because future humans, descendants of this civilization, will look back on you as part of their cosmic heritage. The Milky Way is vast, but it's not an empty vastness. It's filled with matter and energy and structure and history. And it's filled with the potential for consciousness to emerge and understand itself. You're part of that emergence. You're part of the universe's awakening. You matter. And here's what I hope. I hope this video changed how you see the world. Not in a depressing way, but in an awe-filled way. I hope when you look up at the night sky, you see not just distant points of light, but neighbors. Other suns, other planets, other potential homes for consciousness. I hope you feel the awe. I hope you feel the connection. I hope you feel the responsibility. When we started this journey, I told you that you're spinning through space at 67,000 miles per hour, and it would take our fastest spacecraft 230 million years to cross our galaxy. I told you that the observable universe contains hundreds of billions of galaxies, each with billions or hundreds of billions of stars. I told you that you would never look at the night sky the same way again. And I hope that's true. But I also want to tell you something hopeful. Yes, the universe is vast. Yes, you're small. Yes, your time is limited. But that doesn't mean you're insignificant. That doesn't mean your life doesn't matter. Your consciousness matters. Your curiosity matters. Your compassion matters. Your attempt to understand the cosmos matters. In a universe of billions of galaxies and trillions of stars, you exist. You're aware. You're capable of understanding. That's extraordinary. Thank you for spending this time with me. Thank you for going on this cosmic journey. Thank you for letting me help you understand your place in the Milky Way. If this video resonated with you, if it changed how you see the cosmos, please hit that like button. Tell me in the comments where you watched this from and what cosmic questions still burn in your mind. And subscribe. Please subscribe, because we've only scratched the surface of what the universe has to teach us. There are so many more mysteries to explore, so many more revelations to share, so many more moments of awe waiting for us. The cosmos is calling. Are you listening? Over the next sections, I want to spend some time with you on this reflection, knowing that some of you are feeling the weight of cosmic insignificance, and I want to help you feel the weight of cosmic significance instead. Think about what we've established. You are conscious. In a universe that was unconscious for billions of years, you are conscious. You can think about the Milky Way. You can understand the cosmos. You can feel awe. That's not insignificant. That's extraordinary. Every human who's ever lived has wondered about the stars. Every culture, every civilization, every person who's ever looked up at the night sky has felt something: awe, wonder, curiosity, a sense of connection to something larger. That's not a universal experience because we're all insignificant. It's a universal experience because we're all connected to something profound. We're all part of the same cosmos. We're all made of the same matter. We're all subject to the same laws of physics, and that connection is real. It's not metaphorical. It's physical, chemical, biological, real. So when you feel small looking up at the night sky, remember that smallness is precisely what connects you. In your smallness, you're like every other conscious being in the universe. In your finitude, you're like every other creature that's ever lived. In your uncertainty about your place in the cosmos, you're expressing the fundamental question that consciousness asks of existence: where do I fit? And the answer is, you fit everywhere. You're part of it all. You're not a separate observer looking at the cosmos from outside. You're a participant in it. You're a localization of the cosmos's attempt to understand itself. That's your significance. Now, you might be watching this in your bedroom. You might be watching this on a crowded train. You might be watching this in a country far from where this was made. But right now, you're all looking at the same sky. The same stars that guided ancient explorers also guide you. The same light that left distant galaxies billions of years ago reaches your eyes. We're connected through that light. We're connected through the shared cosmos that gave us birth. We're connected through the common awe that the scale of the universe inspires. And that connection is what makes us human. Not our technology, not our civilization, not our achievements. Our ability to look up at the sky, to understand that we're part of something vast, and to feel connected to it. I'm deeply grateful that you spent this time with me. Grateful that you let me guide you through the cosmos. Grateful that you're the kind of person who wants to understand your place in the universe. Because people like you, curious, humble, willing to contemplate the vast scale of existence, are the hope of the future. You're the people who will carry consciousness forward. You're the people who will ensure that the universe's gift of self-awareness continues. Thank you. From the bottom of my stardust, thank you. Now, I know we've covered a lot. We've gone from the basic scale of the Milky Way to the far future of the cosmos to your role in all of it. Some of you might be reeling. Some of you might be ready for more. Some of you might just be staring at the stars, contemplating everything we've discussed. All of those responses are valid. If you have questions, please ask them in the comments. If you want to discuss cosmic mysteries, I'm here for it. If you want to know more about any of the scientists we've discussed, Hubble, Rubin, Perlmutter, Weiss, Schmidt, let me know, and I'll make more videos diving deeper. If you feel moved to learn more about astronomy, about cosmology, about our place in the universe, go to your local library or search for courses online. The knowledge is out there. The understanding is available. All you have to do is want it. And if you ever look up at the night sky and feel small, Remember what we've talked about today. Remember that you're made of stardust. Remember that you're conscious in a way that few things in the universe are. Remember that the light reaching your eyes has traveled across billions of light years and billions of years of time to connect with you. You're not small. You're not insignificant. You're a manifestation of the cosmos becoming aware of itself. That's the greatest significance anything could have. Thank you for watching. Thank you for caring enough to learn. Thank you for being conscious enough to wonder about the cosmos. The stars await, and you're ready to understand them.